Hi, I'm Johann, and today I'm going to join you as we dive deeper into our lesson about carbohydrates. Today, our discussion is all about carbohydrate isomerism. Without further ado, let's get started. The word carbohydrate isomerism might be too complex of a topic to understand at first, but that is why we're going to break it down into two simpler terms. The first is the word carbohydrate. When you hear that word, when you think of carbohydrates, what are the first things that come into your mind? Perhaps you're going to think about food, or maybe sugar, or maybe you're going to think about the different molecules and formulas involved in carbohydrates. Now, while all of these are true and valid, what about the other term? What about isomerism? When you hear the word isomerism, what do you think isomerism means? These are the questions we are faced with in this discussion. And today, we're going to answer all of them as we dive deep into carbohydrate isomerism. In line with that, I've prepared 4 learning targets that I'm confident by the end of this video you will be able to master and achieve. First, we're going to define carbohydrate isomerism and its 4 common types. Then, we're going to draw the structures of carbohydrate isomers in different representations. Then, we're going to recognize and explain the structures of aldoses and ketoses. And lastly, we're going to take all the things we've learned from parts 1 to 3 and we're going to relate the topic of carbohydrate isomerism and its applications to one's health and nutrition. To keep these learning targets in mind, our discussion today is divided into 4 different parts. Part 1 is the 4 common types of isomerism in carbohydrates. Part 2 is the different representations of carbohydrate structures. Part 3 are the structures of biologically important aldoses and ketoses. And Part 4 are the applications of carbohydrate isomerism to one's health and nutrition. With all these in mind, I hope that the plan is clear enough for everyone to understand, and I hope that you're ready to keep up with this discussion. Without further ado, let's get started. To begin, we first ask ourselves, what exactly are isomers? We know that they're related to our topic somehow, but what are they? Well, essentially, isomers are molecules. They're molecules that you wouldn't freely find in nature. But to be more specific, they're molecules that have the same molecular formula but different arrangement. So let's take a look at some examples. On screen, you're going to see glucose and galactose, 2 different sugars or carbohydrates. But despite being different, they actually have some similarities. Let's take a look at their structures. By looking at their structures, we see that glucose and galactose actually have the same formula. On screen, we see that glucose has 6 carbon atoms marked in red, and it has 12 hydrogen atoms marked in yellow, and 6 oxygen atoms marked in blue. But the same can be said for galactose. It has 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms. From this, we can conclude that they have the same formula. But after carefully looking at the structures of glucose and galactose again, we realize that there seems to be a difference in arrangement at carbon number 4. At carbon 4, the OH group of glucose is on the right, while the OH group of galactose at carbon number 4 is on the left. This means that not only do they have the same formula, but they have a different arrangement in structure. So we can conclude that these two sugars, glucose and galactose, are carbohydrate isomers. Carbohydrate isomers are when two sugars have the same molecular formula but different arrangement. Again, carbohydrate isomers are when two sugars have the same molecular formula but different arrangement. Now, I hope that's been clear for everyone, and I hope that that lays down a perfect foundation for the next parts of our discussion. Now we move forward to the 4 common types of isomerism in carbohydrates, starting first with stereoisomerism. When we talk about stereoisomers, we refer to the configuration of the asymmetric carbon furthest from the aldehyde or ketone group. In other words, we look at the carbon that is furthest away from the functional group of the carbohydrate. Your stereoisomers are divided into your enantiomers and your diastereomers. Your enantiomers are non-superimposable mirror images, while your diastereomers are non-superimposable non-mirror images. What this means when we say non-superimposable is that they cannot be perfectly overlaid or stacked on top of one another. Your enantiomers, like D-glucose and L-glucose, are mirror images, meaning that they are the exact flip image of one another. For example, your D-glucose and L-glucose have the same structure, except it's almost as if there's a mirror in between that flipped them. But the same cannot be said for your cis-butene and trans-butene. If you look at their structures, even if you did flip cis-butene, it does not equal to trans-butene. Hence, they are non-mirror images and they are diastereomers. Now, we take a closer look at our enantiomers. Our example earlier was D-glucose and L-glucose. But how did they get their configurations? Well, we got that by looking at the penultimate carbon, which is the second to the last carbon. In this case, it's carbon number 5. If the penultimate carbon's OH group is on the right, a carbohydrate is said to have a D configuration. If the penultimate carbon's OH group is on the left, it's said to have an L configuration. If we look at D-glucose and L-glucose again, we see these. We see that the OH group of the second to the last carbon is on the right, hence it's D-glucose. And for L-glucose, the OH group is on the left. This is important to note because for most monosaccharides, they exist in their D forms. So in nature, the D forms of your carbohydrates are more abundant than their L counterparts. Here are some more examples. We have D-fructose and L-fructose, which are enantiomers, and glucose and galactose, which are diastereomers. So by looking at the penultimate carbon, we see that the OH group of D-fructose is on the right, and for L-fructose, it's on the left. However, for glucose and galactose, they aren't mirror images of each other, and they're non-superimposable. Hence, we know that they are diastereomers. So now we move forward to aldehyde isomerism. Recall that carbohydrates can be classified by their functional group, and we do so by calling them aldoses and ketoses. What this means is that your carbohydrates can either be an aldose or a ketose, depending on the functional group they have, whether it's an aldehyde group or a ketone group. Here's some examples. D-glucose is an aldose because it has an aldehyde group of R, C, H, and O. Fructose, on the other hand, is a ketose because it has a functional group of R, C double bond O, and R. Glucose has an aldehyde group Fructose has a ketone group. Now we move on to epimerism. In epimerism, we introduce a new word called epimers. Epimers are essentially a class of diastereomers, and the principle behind them is that they are only different at one carbon atom. So let's take a glucose for an example. Glucose can form epimers mannose, galactose, and allose. And here's how. It forms an epimer with mannose simply at carbon number 2, an epimer with galactose at carbon number 4, and an epimer with allose at carbon number 3. At these carbons, glucose has a flipped arrangement, and so mannose is an epimer to glucose because it's flipped at carbon 3. Galactose flipped at carbon number 4. Mannose was number 2. And allose at carbon number 3. Hence, all of these are epimers of glucose because again, they only differ in the arrangement or configuration of one carbon atom. Now is the last but not the least common type of isomerism, which we call anemorism. In anemorism, we refer to the configuration of specifically the anomeric carbon. And what's that? Well, for aldoses, it's simply carbon 1, and for ketoses, it's carbon number 2. So, here's some examples. Alpha-D-glucose and beta-D-glucose. Alpha-D-glucose is in its alpha anomeric form, and this is because its OH group is on the opposite side of CH2OH. Beta-D-glucose is on its beta form because the OH group is on the same side of CH2OH. You could also think of it this way. Alpha is down, beta is up. Now, why is this important? We've already discussed stereoisomers, we've discussed epimers. Why now anomers? It's because of mutarotation. Mutarotation says that in solution, the alpha and beta forms of carbohydrates are spontaneously inconvertible, meaning that they are in equilibrium, and from an open chain, it can change into its alpha anomeric form and its beta anomeric form. Now, that concludes part 1 of our discussion. If you'd like to check comprehension, please feel free to pause the video and take your time in answering the following 5 questions before moving on to the next part of our discussion. Okay, so we've now made it to the second part of our discussion, which is all about the different representations of carbohydrate structures. The reason why we have this is because this is D-fructose. But this is also D-fructose, and this is also D-fructose. So clearly there are different ways for us to draw the structures of carbohydrates, and we're going to focus on that now, starting with our Fisher projections. Well, Fisher projections are essentially what we've already been showing you. It's the one with the lines, with all the atoms laid out, and all the H and OHs. But more than that, they are essentially two-dimensional representations of the open chain structures of carbohydrates. And in Fisher projections, the H and OH groups are placed on the left and right. A good way to remember them is that Fisher equals to fishbone. So looking at the diagram here, it very much resembles bones of fish. But we also mentioned earlier, right, that carbohydrates can exist in their anomeric forms. And there, we use a different structure, which perfectly leads us to our Haworth projections. Our Haworth projections are similar to our Fisher projections, except they are in cyclic form. So they are also two-dimensional representations of carbohydrate structures, but they are in cyclic form. In Fisher projections, the H and OH groups are on the left and right. In Haworth projections, the H and OH groups are at the top and the bottom. Now, this is what D-galactose would look like if it were a Fisher projection converted into a Haworth projection. An important thing to note here is that when converting Fisher and Haworth projections, everything written on the left is written on top. Everything written on the right is written on the bottom. So this is carbon number 2. Carbon number 2 here is over there. And so the H is on the left, hence it's written on top. And the OH is on the bottom, hence it's written on the right side. So here's another example. Let's take a look at D-fructose. In D-fructose, we see that carbon 1 and 2 is here, 1, 2. And this is carbon number 1, this is carbon number 2. Let's focus on carbon number 3. In carbon number 3, the OH is on the left, hence it's written on the top. And the H is on the right, hence it's written in the bottom. So again, left is up, right is down when converting from Fisher to Haworth. Now we go to our chair conformations, which is the third and last representation of carbohydrate structures. Your chair conformations are much like the Haworth projections, but instead they are three-dimensional representations. And the H and OH groups are either axial or equatorial. Axial meaning they're either up or down, equatorial meaning left or right. So take a look at these examples. We have the galactose and the fructose again. This is your axial, meaning it's going up. And this is an equatorial, meaning it's going left or right. Additionally, these are your axial here, axial and equatorial. So in this case, this is very much similar to your Haworth projections, except there's just a tad bit of flair, adding a bit of three-dimensionality. And so, that concludes part 2 of our discussion today. We discussed Fisher projections, Haworth projections, and chair conformations. If you'd like to test your comprehension on part 2, feel free to pause the video once again and take as much time as you need, because the next part of our discussion, we're going to be talking about the biologically important aldoses and ketoses. Okay, so now we've made it to part 3 of our discussion today, which is all about the structures of biologically important aldoses and ketoses. We'll start first with the aldoses. Recall that aldoses have the aldehyde functional group, and so their family tree might look like this. We start first with D-glyceraldehyde, which is the parent compound of all aldoses. We call it the parent compound because D-glyceraldehyde is literally the compound from which all aldoses are made. Because simply what we're doing here is adding a new stereogenic center for every level. And you'll notice that these stereogenic centers are simply opposite to one another. One is on the right and the other is on the left. And the same pattern repeats from the first up to the last, starting with your trioses, 3 carbons, your tetroses with 4, your pentoses with 5, and your hexoses with 6. Now, this is essentially the same pattern for all the aldoses. But what about the other family? What about your ketoses? So for the ketoses, recall that their functional group is the ketone group. And as a result, their family tree might look like this. The parent compound for the ketoses is dihydroxyacetone. And this is significant because if you look at its structure, it has 2 identical attached groups, which means dihydroxyacetone is achiral. And because it's achiral, the family of ketoses generally has lesser stereoisomers than the family of aldoses, as shown in the diagram here. But essentially, the same pattern is being repeated. We start with dihydroxyacetone, a triose, then the tetroses, the pentoses, and the hexoses, where essentially a new stereogenic center is simply added for every level, and they only differ in their position. One is on the right and the other is on the left. Now, I know it's a lot to look at these diagrams, but unfortunately, the best way for you to really sink in all of these structures, both aldoses and ketoses, is to repeatedly study these diagrams. So you have to memorize every structure, memorize every position of the OH groups. At the start, it may be difficult, but as you go along the way, I promise you, it gets easier. And so, that concludes our third topic of today, which is the structures of biologically important aldoses and ketoses. For this topic, I decided to do the comprehension check together with you. So let's check your comprehension. Starting with number 1. Is this carbohydrate an aldose or a ketose? Well, the clue must be somewhere with its functional group. We can see here that this is not the functional group of an aldehyde. This is a ketone functional group, and therefore we can say that the answer to this question is ketose. Alright, there we go. Let's move on to the second number. Is this a ketose, a pentose, or an aldohexose? Well, to answer this question, let's eliminate some of the options. We can already see here the aldehyde functional group. Therefore, it can't be a ketose. And we can also count the number of carbons. Number 1, 2, 3, 4, 5, and 6. And therefore, it can't be a pentose. And so, the answer to this question must be aldohexose. Very good. Let's move on to the next number. Here, what is the main difference between aldoses and ketoses? So we discussed this earlier as we were looking at the family trees of both aldoses and ketoses. And the main difference, again, is their functional group, which is either the aldehyde or the ketone functional group. And so we finally reach the last but not the least of our 4 topics today. We reached the applications of carbohydrate isomerism to our own health and nutrition. So in part 1 of this discussion, we defined what carbohydrate isomerism is, and we also explained the 4 different types. In part 2, we discussed now the different representations of carbohydrate structures. And in part 3, there we learned about the different biologically important carbohydrates which are found in our aldoses and ketoses. That leads us now to part 4, where we take all the lessons we've learned from parts 1 to 3 and we ask ourselves, how do these tie up to our own health and nutrition? In line with that, we prepared here an outline for this topic, starting first with glucose metabolism. So, when talking about glucose metabolism, we take a much closer look at D-glucose. D-glucose, if you didn't already know, is the body's primary source of energy. It's what our cells use to produce ATP, also called adenosine triphosphate. Now, you might be wondering, why is isomerism significant? What does it have to do with anything about ATP production? Well, this is a structure of D-glucose. And on the right, you see the structure of L-glucose. It's an enantiomeric pair. This is significant because our body cannot actually utilize L-glucose for ATP production. Even if we did try, it simply wouldn't work. While D-glucose offers us nutrition, energy, and a lot of other more benefits, your L-glucose provides little to no value. So here we can see the importance of isomerism and how us understanding it can benefit our health. Let's take a look at the next example, which is the digestion of starch. Now, the digestion of starch is another great example of how isomerism is crucial to our health and nutrition. We know that starch is a common polysaccharide found in our food, and so we must pay close attention to how our body digests it. When digested, starch is broken down by enzymes in the body into its smaller monomeric units, which are alpha-D-glucose units. And so, when digested, we can absorb these alpha-D-glucose units into our bloodstream for more energy. But what if, for example, we didn't eat starch? What if we accidentally ate something with beta-D-glucose units? Something that wasn't starch, but instead was cellulose. This is significant because cellulose fibers, when eaten, cannot actually be broken down into smaller monomeric units. Our body specifically lacks the enzymes that break down cellulose into its monomeric units. And therefore, if we were to eat cellulose, we wouldn't actually gain any nutrition from it at all. That's another example of how isomerism is useful in understanding our health and nutrition. Let's move on to the last point of this topic, which is the glycemic index, also known as GI. GI refers to how quickly carbohydrates are absorbed in the bloodstream. And it's important to note that different isomers have different GIs. So say for example, you were eating a meal, a big hearty meal, and let's just say that this meal was rich in alpha-D-glucose and beta-D-glucose. It's important to note that these are anomers. They have different structures and therefore they're isomers. This also means that because they're isomers, they have different GI values, which is significant because this tells us that the one might be more quickly absorbed in the bloodstream than the other. Now, this is greatly significant, especially with high implications to patients with diabetes. And so, that concludes the last part of our discussion today. The last but not the least, talking about the applications of carbohydrate isomerism to one's health and nutrition. As always, here is a comprehension check to see if you fully understood that last topic. And so, that concludes our 4-part discussion on carbohydrate isomerism. Hopefully that you were able to keep up throughout every part and more importantly, learn something that you can relate to your life, maybe as a student, maybe as a medical professional, or wherever you may find it useful. But before we formally end this lesson, let's go over again the learning targets that we had at the start to make sure that we really did achieve these. We had 4 learning targets. The first was to define carbohydrate isomerism and its 4 common types. The second was to draw the structures of carbohydrate isomers in different representations, covering the Fisher, Haworth, and Chair conformations. The third learning target was to recognize and explain the structures of the aldoses and ketoses as we differentiated the family trees of both groups. And last but not the least was to relate carbohydrate isomerism and its applications to one's health and nutrition. So indeed, we were able to cover all 4 of these learning targets. And so, that is it for our discussion today. This has been Johann. Thank you so much, and God bless to all of you who joined me in this wonderful discussion.